So for assignments, this week you have pre-lab 9 coming up for Thursday, and then lab 9 you will be executing on Friday, and then throughout the following week. So take a look at that. There's also a new quiz posted, so that will be due 11/20. That will be on op-amps, so that's also up there on the PDF schedule and on Canvas on the assignments. Just to remind you, I'm unable to add everybody automatically to Slack channels, so you will have to add yourself by searching for the channel like homework 9 or not homework 9, homework 7, homework 8, etc. So take a look on Slack to add those channels. So my office hours will be right after class today, and the TAs are posted. And so stop by, ask any questions you want, or just stop by to listen to other people's questions and discussion. And of course, ask questions during class by unmuting or chatting if I see it. Otherwise, please stay muted to keep the background noise low. So today I'd like to continue with combinatorial logic. We talked about combinatorial logic last time. I introduced logic gates, and I said, really the combinatorial logic problem, or solution, I should say, is this. If you have a decision to make, or you want your circuit to make a decision based on digital inputs, on present time inputs, right? Inputs that happen right now, you can use combinatorial logic to do that. So you have, one or more, usually many inputs into your circuit. I used the example of the car starter. So what inputs would you want to the car starter? So the key is turned, the car is in neutral or park, maybe the brake is pressed, maybe the airbag's not deployed. So you could think of all these true, false, or yes, no inputs, or 1, 0 inputs. That would be Boolean. Those are Boolean variables that go into a circuit, and the output is, well, either 1 or 0. Turn the car starter or don't turn the car starter. So that's a type of decision that combinatorial logic circuits will make. And then I talked about these gates. So we have the AND gate, the OR gate, let's see, the logical inverter, the exclusive OR, and then I talked about the NAND gate and the NOR gate. Okay, and so what I wanted to show you is, okay, great, these are nice symbols, but what does this look like in real life? So this is, these are depictions of, well, actually a photo of several logic chips and their pinouts. So these chips on the lower left are plastic packages, right? With they're called DIP packages, dual inline pins, and these are meant to either plug into a breadboard or a printed circuit board, and they implement logic functions. These look a lot like your op-amp chips. They're the same kind of package. They have just different electronics inside in these integrated circuits. So if we look, for example, at the upper left, this AND gate shows 4 AND gates in this one chip. And so you have the kind of the cartoon of the chip and the pinouts, right? So on chips, it's common to have this notch or some maybe dot, and pin 1 is always to the left of that. Look in the data sheet, but typically it's to the left of that notch, looking from the top. So then you can see this has 14 pins, this chip. So what you do is you, if this is a 5-volt chip, you apply ground to ground, you apply 5 volts to VCC, and then you have 4 AND gates available to you. So for example, this lower left AND gate, pin 1 is an input, pin 2 is an input, pin 3 is the output of this gate. And so if you apply, let's say, 5 volts to pin 1, 5 volts to pin 2, you'll see 5 volts at pin 3. That's what an AND gate does, right? Logic 1 at pin 1, logic 1 at pin 2, you'll see logic 1 at pin 3. If you have a 0 at pin 2 and a 1 at pin 1, then you'll get a 0 at pin 3, which means 0 volts, right? So So you have 4 gates available to you here. Here's a Nand gate right next to it, right? So same concept, power the chip at VCC and ground, and you have 4 gates to use. Here's a what's called a hex inverter, 6, right? Hex equals 6. You have 6 inverter gates on this chip, power it, ground it, and apply inputs, and you get outputs corresponding to the output you would expect. Here's XOR. At the bottom, here's an OR gate. Here's a NOR gate. So you can buy chips that are various speeds, various cost, and they implement gates. So let's suppose you want to build a circuit that makes a decision. That's what I'm going to step into now. And let me stop sharing and go over to the whiteboard. So let's talk about first implementation of Boolean expressions. I mentioned last time that Boolean expressions are, well, equations that use logical variables or Boolean variables, meaning those variables represent 1 or 0. Okay, so let's do an example here. If I have some kind of expression, D equals A plus, remember that's an OR, a logical add is an OR, and then I have B inverse times C. Okay, so here is a Boolean expression. It describes a logic circuit, or I should say a logical operation, really. And let's suppose we want to implement this with gates. So you want to take those chips I just showed you, power them up, and implement this. So here's what I like to do. I like to start, I'll say on the right side here of the circuit. So I'm going to have a circuit here with gates. And on the right side at the output, I want this. I want D equals A ORed with the inverse of B ANDed with C. Yes, you can take words that are normally conjunctions in this class and make them verbs, kind of like text, noun into a verb. So I'm going to start at the output. So this is a wire at the output, and perform the last logical operation or Boolean operation that lost the video, that I want to perform. So what I'm going to do is follow the order of operations. And you can imagine the order of operations is, well, a lot like regular algebra. So I have A plus the inverse of B times C. So if this were just a regular algebra expression, the first thing you would do is multiply B inverse and C together, right? And then you would do the add. That's what we normally do with regular algebra. Well, that order of operations is the same for Boolean expressions. So the last thing I want to do is that add. So let me do that now. That's an OR gate. So there's my OR gate. And at the input of the OR gate, I want, let's see, A, and then B inverse times C, or B inverse ANDed with C. And what I'm trying to do here is I'm trying to get from, right, or to the output from inputs that are just A, B, and C. I assume A, B, and C are the logical values that I have. Okay, so I have A. Let me just kind of draw a big wire here and I say I end at A. That's an input, 5 volts or 0 volts if it's 5-volt logic. Now I have to create this combination of B inverse ANDed with C multiplied by C. So I'm going to use an AND gate. So this is my AND gate. And at one input, I want B inverse. The other one, I want C, right? So now I have C, that's an input. I can apply 5 volts or 0 volts for 5-volt logic as an input here. And I need B inverse, so I can just use a logical inverter like that. Okay. So if I, I haven't told you anything about what's the practical application of this. Well, we'll get to that. But once you have your equation, you can create that Boolean equation, Boolean expression with logical gates, just like I showed you on the slide with electrical components. Okay. Any questions on that?
Professor, you got a question in the chat.
Oh yeah, let's see. So that would give the inverse of BC, not the combo of B inverse ANDed with C. So the inverse applies first, right?
Okay, so Andrew asked about using a Nand gate.
Oh, okay. Oh, I see. The one before that. Okay, I thought that was a question. A Nand gate. You mean for the yeah, for this. So let me show you that. So just to show you, if I use a Nand gate and I put B here and C here, then I get B, C, like that, right? So the inverse applies to the whole after I've ANDed B and C together. And even if I invert C before, then I still get something like this, right? So yeah, that I wouldn't recommend doing that. There might be some way you could use multiple gates with the NAND gate to get the value you want, but I wouldn't use this. Okay, other questions on this?
Professor?
Yeah.
So would it normally be the case where you're given like a Boolean expression like this and then you like show the gates or circuitry like from that expression?
Yeah, actually, so what you really start off with is in your application a truth table. And I'll show you that, but you go from the truth table to a Boolean expression, and then a Boolean expression to a circuit.
Okay.
Yep.
All right. Thank you.
Mm-hmm. Okay. So what I want to show you next is actually another use of a truth table. Proving. I can't spell. So I want to talk about proving equivalence using a truth table, just to show you a couple things. One, you can demonstrate that Boolean expressions are equivalent, just like certain algebraic expressions are equivalent in regular algebra. And also that Boolean expressions can be reduced to a simpler form. And this is a way to prove that, and it's also an exercise to start practicing with Boolean variables. Let's say that I have this expression. So I want to implement A ORed with B, that quantity, and then I have another quantity here, A inverse plus AB. And let's suppose I want to implement that in a circuit. And you come along and you say, wait a minute, that looks fishy. I think that you can rearrange that to get a simpler expression. And you say, well, I think you're really not depending upon the value of A. You're actually just looking at B with this expression. So in other words, A doesn't really do anything here. It drops out, and you're really just left with making your decision based on B and not A. So we're going to prove that these two expressions are equivalent, the left side and the right side. And I'm going to do that with a truth table. So let's define the inputs to be A and B. And then I'm going to create a table here. And on the right-hand side, what I'm going to do is create some intermediate expressions that are involved in calculating the left-hand side. And finally, I'll have the left side evaluated and what the logical values would be as a result of these different combinations of inputs on the left. So let's list out the possible combinations, all possible combinations. So you start at 0, you start counting up. So I've exhausted all possible combinations. Okay, let's start evaluating this expression on the left here. Let's start with A plus B. Okay. So let's OR the inputs A and B. A ORed with B. Okay, so if you go back to the truth table, you will see that 0 ORed with 0 is 0, right? The OR gate answers the question, are either or both of my inputs true? So 0 ORed with 1, 1, 1 ORed with 0, 1, 1 ORed with 1, 1. Okay. Okay, let's keep building up these terms here. Let's now evaluate A inverse. So I just invert A, so I get 1, 1, 0, 0. Okay, let's continue on. Let's do A and B. So this term right here. Okay, so the AND gate asks the question, are both of my inputs true? So no, 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 yes. Okay. Okay, now we can put these two terms together to form the term on the right-hand side here, this term in parentheses. So I want to evaluate A inverse ORed with A, B. So this right here. Okay, so now I look at, actually the input now are these intermediate terms. So I'm looking at these two columns here. So let's OR this value, A inverse, with this value, A and B. So that's going to be a 1, 1, 0, 1. Okay. All right, so what we're getting here is for take these rows one at a time. If you apply 1, 0, you're going to get 1 for this term, you're going to get 0 for this term, you're going to get 0 for that term, etc. So you can see the response to the different combinations of inputs. And finally, A ORed with B ANDed with A inverse ORed with AB, that quantity. Okay, so now we are looking at this column and this column, and we are ANDing those together. So I get 0 and 1, 0, 1 and 1, 1, 1 and 0, 0, 1 and 1, 1. Okay. So the result of putting A and B into this left-hand expression and varying the values over these values, this would be the result. So you could see that, well, if I look at the result of that left-hand expression here, it exactly matches B. Right? So no matter what value A is, the value of this on the right, this expression on the right, always equals B. It's always the same. So what we've done is with the truth table, we've proven that this complicated expression on the left really is just equivalent to B. And this is one way of doing that.
And this, I just want to make sure this is the like kind of equation form of the last circuit that you drew. Is that correct?
This is actually a different equation. The last circuit that I drew, it was something like D equals A plus BC, something like that.
Okay.
Yeah, this
Would
is just
we
a different
need
equation.
to learn how to like transfer it from the equation to the circuit and vice versa, or is that a little bit out of the scope?
Yes, yes. So that's exactly what this was, right? This is what we did implementing that last equation in the circuit. Okay, and if you wanted to go to the other way, you could start here and then work forward, or you'd say, okay, B, and this is B inverse, and this is C, so that's, you'd have to form the equation going forward. So yes, you would have to do that.
Okay, thank you.
Mm-hmm. Other questions on this? Okay, so that's right, a bit all sort of academic. I mean, it's useful, but we haven't really applied anything yet. Let's figure out how to create a useful expression. So create a useful expression, which then you could actually make into a circuit. So this is called synthesis of logic circuits. Synthesis means to create something. If you synthesize a filter, you create a filter to meet specifications. If you synthesize a logic circuit, you create a logic circuit to do something that you want it to do, okay? So let's start out with a truth table, and I'll show you where I'm going here. Spread this out a little bit. Let's suppose that I have 3 inputs. These are 3 inputs on the left. And I have an output. This is an output on the right. And I have an idea in mind. Maybe, this could be 3 sensors on a car. It could be the brake pedal is pressed, the car is in neutral, and the key is turned or something like that. Well, when you have 3 inputs, you have to decide what do you want the output to be for each of the 3 inputs. So you start off with, well, a truth table, and we have to list all possible combinations of the inputs. So again, you start at 0, and you start counting up in binary. All right, so I'm just counting up. This is 0, 1, 2, 3. I'm reading it off in decimal. So 1, 0, 1. Okay, so something like that. And then what I like to do, I'm going to draw some lines here because I'm going to keep my values all straight. No significance to those lines other than just dividers. Okay. So, you know, you could decide when the key is turned and the car is in neutral and, you know, the hood is up and the trunk is closed, you know, it doesn't matter. You can decide there's some output that you want to happen. And that's something you decide, or someone tells you, right? Someone might tell you, well, I want the indoor dome light to go on when there's this set of inputs. That's fine. But if you're designing something yourself, right? I want the yard sprinklers to turn on when it's afternoon afternoon and it hasn't been raining and the dog's not outside and you have a dog sensor in your backyard, right? So you decide what the output is. And so let me just say that for this combination of inputs, I want this to happen, right? I'm not really thinking about what the application is. I'm just making up some outputs. So right, for this combination, I want something to turn on. For this combination, I want something to turn off. Here, I want something to turn off. I want something to turn off. Here, oh, I want it to turn on. I want something to turn on. So I have the inputs on the left and the output on the right. And that's great. You can describe this, like that's half the battle, describing the problem. But now you want to implement that. And you want to implement that, let's say, in hardware with those chips. And this is this is one way to do that. And by the way, you could implement this in software also. We're going to get to microcontrollers probably later today, but you could implement this as a Boolean expression in software or hardware. It doesn't matter either way. This still applies, but we still need that Boolean expression. There are two different, I should say, two related approaches, distinct approaches that you could use to do this. One is called the sum of products. So this is the sum of products approach. And then we're going to have another approach called the product of sums approach. But let's work on this first. What we're going to do here is we're going to write terms. We're going to write down terms. D, the output, equals something. Okay. Actually, let me erase that for a second. Put it down here. I'm going to write something on top, but D equals something. And these terms on the right-hand side of this equal sign are going to be terms that force the output to be 1. So I'm going to concentrate on the rows for which the output is 1. And it's going to naturally fall out, you'll see, that where you have inputs for which the output should be 0, that's just going to happen. And I'll show you how that works. So let me write that down. Concentrate on output equals 1. Okay. So this is a sum of products approach. So I'm going to have, well, sums of products. Let's call this a product term, right? Let's say there's some multiplication going on in there. And I'm going to sum that with other product terms. Right? So I'm summing it with other product terms, ... Don't know how many yet. Okay. The key here is that if any one of these terms in parentheses becomes a logical 1, that forces D to be a 1, right? If this is an input, if these are inputs to a multi-input OR gate, the OR gate answers the question, are any of my inputs true? A multi-input OR gate. Or you can create a multi-input OR gate with 2 input OR gates. But the point is that if any one of these terms becomes a 1, and the rest are 0, it doesn't matter, D is forced to be a 1. Okay, so I'm going to look for a way for each one of these rows for which the output is 1 to make a term that causes a 1 to happen. Okay, let's do that. let me move over here a little bit. D equals, okay, my first term. I want a product term that makes a 1 happen for the inputs A equals 0, B equals 0, C equals 0. I can do that by doing this. I can multiply A inverse by B inverse by C inverse, right? I've taken each one of those zeros, I've inverted every one of those. That means I'm ANDing the values of 1 together, right? 0 inverse, 0 inverse, 0 inverse. Now I have 1 and 1 and 1, and that causes a 1 to happen. So for this row, for this input, this set of inputs here, I've caused a 1 to happen. That's good, I want that. Let's go down to the next row for which the output is 1. Okay, so I have this row here. Okay, I have to, with this kind of product term, I have to make a 1 happen, right? So I'm going to invert A. I'm going to leave B alone. I'm going to invert C. I'll get something like that. So when this set of inputs happens, right? A is 0, B is 1, C is 0. I will get 1 ANDed with 1, ANDed with 1. That's a 1. And again, it doesn't matter what the other inputs are, the other terms in this product of sum of products. I will get a 1 for D. So you keep going down. Okay, my next row for which the output is 1. I have to leave A alone, leave B alone, invert C. Right? So when I have 1, 1, 0, 1, 1, invert 0, I get 1. Again, here's a term that evaluates to 1 for this row down here. Okay, so let's do the last one. 1, 1, 1. A, B, C. Okay. So you could see that I have, for every row for which the output is 1, I'm going to have a 1 occur in each one, in one of these terms. It's going to happen. And then D will evaluate to be a 1. So I've made that part of the truth table happen. Well, how about the rows for which the output is 0? Well, the AND function takes care of that. If you try, let's say this row here, 0, 0, 1. If you try 0, 0, 1 in any one of these terms, well, they're all going to evaluate to be 0. Okay. And again, you could try any one of these rows, any one of these sets of inputs for which the output should be 0, and you plug those values in to these 4 terms, and they will evaluate to be 0. Okay.
Is that just because they will not satisfy any of the situations where D should be 1?
That's right. That's right, because we forced the only way that, let's take this term, the only way that A inverse, B, and C inverse, when they're ANDed together, the only way that evaluates to a 1 is when A is 0, B is 1, C is 0, right? So that's A is 0, B is 1, C is 0. So that, Siri keeps listening to me. So that happens only for that one row. Does that make sense?
Yes, thank you.
Kind of piggybacking off of that, when you have a logic circuit with more than, say you have like 20 inputs, and I'm just curious how you would denote which AND expression goes to which row. Does that make sense?
Which AND expression goes to which row?
Yeah. So like when you have A inverse, B inverse, C inverse right there.
Yeah.
That only applies to 0, 0, 0 to 1, right?
Yes, that's right.
So if you have, like 20, you say you go A through Z for your inputs, would you want to kind of denote which one of those terms goes with which row?
You could. The problem is if you had 20 inputs, you're going to have 2 to the 20th, right? 2 to the 20th rows here. So you probably, if you truly have 20 inputs, and like cars have lots of sensors and inputs into logic circuits, what I would do is I would break the problem down into sub expressions. Okay, so what do I mean by that? I mean, like, for example, you have maybe a temperature sensor on the engine, and you have RPM, and you have a bunch of other sensors on an engine, oil pressure, water, maybe, just different values. What I would do is I would first create a circuit. If you care about the engine is running, right? I would first create a circuit that uses all of those inputs to create a Boolean variable that is the engine is running. And so I'd reduce the problem down into sub-circuits instead of trying to handle it all at once.
Okay.
And I mean, theoretically, you could do it. If you had 20 variables, you'd have 2 to the 20th rows. That's a really big number. And you could do it, and you'd have to track, but I would break the problem down into sub-circuits, yeah.
That makes sense. Okay, thank you.
Sure. But just to show you here, right? So how do you create these kind of three? Let's say, let me use X, Y, and Z, so I don't use the same variables. But hey, that's a 3-input AND gate, right? Well, how do you do that? Well, that could be an AND gate. They actually sell these. Like, has 3 inputs, and all inputs have to be true. Like, here's X, Y, Z, I don't know, Q, something like that. Or you can draw parentheses. Suppose you don't have 3-input AND gate. You can draw parentheses around 2 of these and say X, Y goes into an AND gate, right? Here's X, Y, right? That's X, Y. And that is ANDed with another input Z. So here you get X, Y, Z. So you could do the same thing with OR gates. You can use 2-input OR gates, right, to create a single OR gate equivalently with multiple inputs. This is how you do it with an AND gate. Okay.
I have a question.
Sure.
Is there any particular reason why like we want D to be 1? Like I understand the process. I just don't understand like why.
Oh, like why? Yeah. So I just made this row, this column up here.
Okay.
If it was, this could be, for example, key, airbag, and brake, right? Those could be inputs, and then this would be start, right? And so you could list all combinations: key, airbag, brake. The key is not turned, the airbag is not deployed, the brake is not pressed, and then keep going down, right? You can keep doing that, and then decide here, I want the car to start, no. I want the car to start, no, because the key's not turned. So you would define, based on the inputs, what you want to happen.
Okay, so then this equation for D, like how does that come into play if like no matter what we plug in here, we'll get a 1 for D?
Well, so if you put in into each one of these A, B, and C's, right? If you put in 0, 0, 0, so A equals 0, B equals 0, C equals 0, A equals 0, B equals 0, C equals 0, right? And you put that into this equation, it's going to result in a 1 for D.
Mm-hmm.
If you put in 0, 0, 1, it's going to result in a 0 for D.
Okay, so basically it's just the equation for the decision of D.
That's right. We have made this truth table into a logical equation.
Okay, awesome.
Mm-hmm.
That makes
That's
sense.
right.
Thank you.
Yeah.
And so like the, I guess simplest case, if you had, a lock and you have to turn 2 switches on and 1 switch off, there would be just one case where D is 1, and in all other cases it's 0.
Yeah.
I guess.
Right.
And so
Yeah.
like,
Mm-hmm.
do they use these in 7-segment displays?
Yeah, you could actually create a logical circuit to go from a binary number to a 7-segment display. Yes. Like if you have a 3-bit number, which will represent, well, I guess you'd have to use so you need to go up to 9. So you'd need a 4-bit number. You can map that to what each individual segment of the display, whether it would be on or off.
Gotcha, thanks.
Okay. So I'm going to erase this right here. I'll leave this here for a second. there's a way that your book describes these terms. So I want to call it out because it's in the solutions. This is the answer here. This implements this table. Each one of these terms, each one of these product terms is called a min term, M-I-N-T-E-R-M. And so you could say that D is the sum of min terms. Okay, so it's going to be the sum of these terms that are the script M. What I do on the right, on the left here of the table is I assign an index corresponding to the binary value converted to decimal. Okay, and then I write that any value for which the output should be 1, I make that an argument of this min term. So 0, 2, 6, and 7. Okay, so this is just another way, if you already know how your inputs are ordered, to express this equation. So I will generally explicitly write out the variables. Your book solutions are going to show something like this. Okay. Let me show you the other approach, very similar. Product of sums. And the product of sums, well, uses a product of sums to build an expression, and you're going to concentrate on the output equals 0. We're going to force zeros to happen. And the way I do this is this, D equals. So I'm going to have the product of these terms. So here's a term, here's a term, here's a term, dot, dot, dot. So these 3 terms in parentheses, and maybe more, are inputs to an AND gate, a multi-input AND gate. They all have to be 1 for the output to be 1. And if any one of those is 0, it forces the output to be 0. So all we have to do is create a term, let's say for this parentheses right here, that corresponds to one of these rows where the output's supposed to be 0, and make a 0 happen. And it's easier to do than explain. So I'll show you by example. So D equals. So let's go down to the first row for which the output should be 0. Okay. I want to make a 0 happen with some terms, S-U-M, some terms. So I'm going to say, well, just check out this term, A plus B plus C inverse, right? A plus B plus C inverse. All of these A, B, and C inverse would then be zeros, ORed together. So I've forced this first term to be a 0. Okay, let's go down to index 3 here, 0, 1, 1. So I have to make a 0 happen out of a sum term. So 0, right? If A is going to equal 0, B, I want to force that to be a 0. So I'm going to invert it. It's a 1. I want to force it to be a 0. Here's C. I want to force it to be a 0. Okay, so for this set of inputs, 0, 1, 1, I'm going to get 0, 0, 0, ORed together. In the grand scheme of things, you get a 0 in any one of these terms. You force D to be a 0. And you continue on. Let's go down to, let's see, I just did this row. How about this one? A inverse, ORed with B, ORed with C. And finally, see, 1, 0, 1. I have to invert A, leave B alone, and invert C. Okay, so you can go down and you can check this. For all of the 0 output rows, this expression is going to evaluate so that D is equal to 0. Now, for all of the rows for which the output is 1, you'll notice that that's going to cause a 1 to happen in every one of these. Right? So, try 0, 0, 0, 0, 0, 0. Well, that's going to be a 1 for C inverse. I'm going to have 1s show up in this sum. I'm going to have 1s show up in this sum. Right? So each one of these sum terms is going to evaluate to a 1 when D equals 1. Okay. So this is another way of writing an expression to represent this truth table. These are equivalent. Both of these expressions are the same thing. So we're not going to get into manipulating Boolean expressions, and you could say things like, well, if I multiply all these out, or if I factor some values out here, I might be able to simplify. Yes, you can definitely simplify these expressions. You don't need this many gates. There's different techniques to do that. When you only have a few inputs, you can use things like Carnot maps, and there's other ways to do this. I just want to show you this. My point out of this is that you can take a table where you've defined the output based on digital inputs, and you can create an expression, right, either way, and then you can go implement this in hardware to make a decision really fast, make something controlled, or you can program this into software. You can write this expression in MATLAB. MATLAB has logical operators. Do that in MATLAB, or C, or Python, or anything. Okay, so let me just, another notation on how the book is going to show you answers. Each one of these sum terms is called a max term. Right, so D is equal to the product, so capital Pi is, right, product like capital sigma is a sum, capital Pi is a product. You're multiplying together. This is a capital M, this is a script M. Let's see, 1, 3, 4, 5. So that's how the book's going to show the answer. Okay, questions on that?
Professor, I think you got a couple questions in the chat.
Oh yeah, okay. Let's see. How?
Oh, you just answered mine, I think.
Oh, did I? Okay, good.
Yeah,
Good.
thank you.
Okay. So what I'm going to show you now is this. So now great. You can make decisions with electronics, right? These decisions based on binary values. So what if you want to do something like math, right? Let me bring something up here. So what if you want to do something like implement a mathematical expression? And let's use a sum. You want to add two numbers, two integers, keep it easy. What I want to show you is how these gates are made. How a logical gate like an AND gate or an OR gate or an inverter is created out of transistors. You already know transistors can be created out of switches. Well, I can show you how to take switches or transistors that are controlled by inputs and make these logical gates happen. And so what I want to do is I want to take you from transistors, right, to gates. And then I want to take you, okay, if you understand how to build a gate, I want to take you to math operations, like addition, for example. And so then you could actually see that you can take transistors, right, with a base resistor, collector resistor, and saturating that transistor. You can take these transistors like you've been using and actually add binary numbers together. Okay, so that's what I'm going to take you through. Okay, it is 6:10, and so we'll end right here. Don't forget pre-lab 9 and lab 9 are posted, and so take a look at those. They will be executed this week. Take a look at the quiz. It's posted. It's not due until 11:20, but don't miss that. That's up there, and it's on op amps, so it might help to do that while op amps are fresh in your mind. So thanks for joining class. I will hold office hours in a minute. I hope everything's working out well. Please let me know if anything's not working out well so I can improve it. And if I don't see you at office hours, I will see you next time. Have a good night.